What's going on, guys? Hope you're doing awesome and welcome back for another video. In the last video, we implemented a sequence-to-sequence model on the task of translation. And in this video, I want to improve on that model by introducing this idea of attention. So, before we get to actually implementing this, let's try to first convey the intuition behind this important idea. So this is the figure I used in my last video where, we have our encoder and it produced this context vector, and we had this decoder which takes as input this context vector. Well, one thing we can imagine is that if we have very long sentences, then this context vector is going to become a bottleneck in that if we're very far along from the beginning of the decoder, from the where the context vector is sent in, then we might not remember what the context vector actually said. So this figure right here is sort of conveying the intuition of what we're going to do. Instead of just having the context vector be sent as input to the decoder, we're going to have a context vector which is sent to every cell of the RNN. All right, I don't want to spend too much time on this figure because I don't think it's very good. So I want to show this one right here first. So we have the blue score on the y-axis and we have the sentence length as our x-axis. And so using these, these sequence models we implemented in the last video, the problem is that it loses, the blue score if the sentence lengths are very long, which resembles this idea that it's losing attention. It's losing it's not able to memorize what the source sentence actually said. By implementing this with attention, we can see that even though we have very long sentence lengths, we can still maintain a high blue score. So I want to go up here and try to explain how this works. And I think most of this is going to be clear as well in when we actually start coding it. But it's good to have a first idea, and I'm also going to link a couple resources that I think are great if you want more in-depth explanation. So I'm going to explain from this figure from the paper, and I think a lot of we have this encoder right here at the bottom, which is going to be a bidirectional RNN. So it has hidden states going from the left, and it has hidden states going to the right. So and then we have our encoder right here at the top, which is trying to predict the target words y/t for a specific time step t. So let's say that we're translating a sentence and we are translating the last word of that sentence. Then it probably makes sense that we want to keep in our memory, or try to remember what the source sentence said on the last few words. So what we're going to do when we send the context vector to this this last time step, then we're going to multiply these hidden states from the source sentence with this attention score values right here, these scalar values. And so these attention score values are going to be element-wise multiplied with the hidden states, and they will signify how much are we going to pay attention to this hidden state from the source sentence. So let's say that we're translating the last word, then we would probably want to pay most attention to one of these last couple of words. So let's say this last attention score will probably have a very high value. So we element-wise multiply these attention scores with the hidden states from the source sentence, and these attention scores are specific for this time step t. So we're doing this for every time step. And the sum of all of those attention score multiplied with the hidden state is going to be summed up, and that's going to be our context vector, and that is going to be sent in to the step in our decoder. All right, hopefully that was clear. But you might have one question still, which is how do we compute these attention scores? And so from the paper here, what we do first is that we compute these energy states from a function a, which takes as input si-1, which is the previous hidden state from our decoder, when we're actually trying to translate, and then the hidden state from the encoder. So this A function is going to be a small neural network, like a one-layered neural network, for example. And what this is trying to learn is which hidden state should we actually pay attention to. So I said that if we're at the last word in a sentence, we would probably pay more attention to the last words. But that's just my intuition. We're going to have the neural network actually learn this from a small neural network by itself. And then we're going to take these energy states and we're going to run it through a softmax. And this is going to be, the output from that softmax is going to be these attention score values. So the great thing about running it through a softmax is that it's now going to be normalized. So the sum of attention is going to add up to 1. So essentially, if an attention score is 0.8, then that means that we're paying 80% attention to that hidden state. And then lastly, to produce a context vector, as I said before, we're going to element-wise multiply our attention scores with our hidden state. And so yeah, I'm going to link you more in-depth explanation in the description, and I think a lot of this is going to become more clear when we actually start coding it. So let's go and try to code this now. So what I have here is the code from the last video. So I don't know how many lines this is, but it's like 225 lines that we wrote in the last video, and I don't want to repeat all of this again, since we're going to just build on this code. So if you want to know how to build a sequence model, watch my last video, and in this video we're going to expand on that video and add this this attention part. All right, so we're going to start in the encoder, and what we got to do is we got to add this bidirectional. So we're going to do bidirectional equals true. And now what's going to happen is that this hidden and this cell is going to have one extra dimension, since it's going to have one going forward and one going backward. And it wasn't super clear to me in the paper if what they did. I think they just used one of them. So the one going forward, for example, they just took that one and then sent that to the decoder, which is not going to be bidirectional. So to have the shapes add up, what I did is that I added 2 fully connected layers, and essentially we have our hidden size, but since we have bidirectional, we're going to have 2 times that, and the decoder is just going to take hidden size times 1. So I was thinking we can do a linear layer which just takes these 2 hidden states from forward and from backwards and send them through a linear layer, and this linear layer can itself choose, the network can choose what's important for actually if the forward or the backward, and choose the most relevant parts. So instead of limiting the information to just forward or just backward, we send it through a linear layer. All right, hopefully that was clear. And then we're going to do the same for the cell. So we're going to do and then linear, and then it's also going to be hidden size times 2 and hidden size. And so all we got to do then is, when we send it through the RNN right here, is that we got to compute this new hidden as self.fullyConnectedHidden of torch.concatenate, and we're going to add hidden, the first hidden, which is for the forward one, and I'm going to do 0 to 1 just to keep the dimensions. And so we're going to do 0 to 1 and then hidden 1 to 2. All right, this will be the hidden states for the one going forward. This will be the hidden state for the one going backwards. And then we're going to do dimension equals 2 because we want to add so this will be, I think the shape of this is going to be 2 comma n comma hidden size, like this. And so, when we concatenate them, it's going to be 2 times the hidden size. So we just concatenate that dimension and send that through the fully connected layer. And then we're going to do the same for the cell state. And again, you don't have to do it this way. It was a little bit unclear to me just how the paper did it, but this definitely works. You can also just take the forward one or the backward one and I guess check and see which one does the best. But so we're going to do this for the cell state as well. So in this way, we're not losing any information necessarily. We just let the neural network choose by itself which one it thinks is best. And then, so we're going to change this to the encoder states. And so we're going to output this encoder states because, we want the hidden states for each time step, right? And this hidden right here is just outputting it's only outputting the rightmost hidden one. It doesn't have a hidden state for each time step. That's what encoder state has. But we need to send in, all 3 to our decoder. And so this one is, let's see in the paper. So the encoder states are these HJ right here, since they are, specific for the time step. As we see here, we have a hidden state for each time step, and that's exactly what these encoder states right here are going to be. All right, so what we then want to add in our decoder, we're going to have our embedding, we're going to have our RNN, but the RNN now is going to take in hidden size times 2 plus the embedding size. So why this makes sense is because we have the encoder states, which has a forward one and a backward one. And since this is, both of them are included in the first hidden, like a specific hidden state from our encoder, then it's hidden size times 2. And we're also going to send in the embedding size. So we're just gonna, so this will be from the context vector from the encoder, and this is just going to be as normal. We're just going to send the embedding as we did in the previous video. So then what we want to do is we want to add let's see here. So we want to add self.energy, and we're going to do this, what I mentioned previously, a small neural network. So we're going to do hidden size times 3, 1, because here we're going to first add the hidden states from the encoder, but we're also going to take the hidden from our previous step in our decoder. So in the paper they said SI minus 1 and then the HJs, so that's why it's times 3 right here. And then we're gonna do our so we already have the fully connected. We're just going to define our softmax, and it's going to be nn.softmax of the dimension 0. So this is going to make sense exactly why it's dimension 0 later. And then we're going to do self.relu is nn.relu. And so what we got to do now is we got to first, compute our goal is to compute these attention scores, right? But what we got to do first is we got to compute the energy states. So to compute the energy states, we want to send in the hidden states from our encoder and also, the hidden from the decoder. And well, this is a bit confusing maybe, but hidden here is from the decoder. And then what we're going to have is we're going to have another, which we're going to call encoder states, just to not confuse the hidden from the encoder and decoder. This is from the encoder and this is from the decoder. We want to add them together, concatenate them, and then send them through this energy layer right here. And what we got to do first is we got to do first get the sequence length, which is the encoder states.shape 0, and then we're gonna do a reshape of these hidden states. So we're gonna do hidden dot repeat sequence length, comma 1, comma 1. So essentially, So we have this encoder state, which is for all of our hidden time steps. But to add them together, we need to have this, have the same dimension along that axis. So we need to, repeat that, the hidden state from our decoder sequence length times to be able to concatenate them together. So when we have this, we're going to compute energy by self.relu of self.energy torch.concatenate, and we're going to send in this h reshaped and the encoder states, and then we're going to add them along dimension 2. Essentially it's going to be then hidden size times 3. So I guess this one has hidden size times 2 because it's bidirectional, and this one just has hidden size, and we're concatenating them and we're sending them through this energy layer, and then we have these energy right here. Then we're going to compute this attention values by doing the softmax of the energy. And I think so attention here will be shape sequence length comma n comma 1, and that's why we also have the dimension equals 0, which is we're gonna normalize through the sequence length, essentially so that the sum of the attention scores will be 1 for a specific batch, because we have a batch size of n sent in simultaneously. So then what we want to do, so our goal right now is to element wise multiply the attention with the encoder states, but to do that we gotta first do a little bit of a reshape. So what we're going to use is we're going to use torch.bmm. If we look at the encoder states, then they're going to be n comma, or let's see, essentially the encoder states are going to be 3-dimensional tensors. So to be able to multiply in the way that we want, which I'm going to explain how we do in just a second, but that's why we use torch.bmm just for these 3-dimensional to do the matrix multiplication essentially. So we're going to do attention equals attention dot permute 102, and then so what we have after this is we have n comma 1 comma sequence length. All right, so we just swap the order, and we're going to do the same thing for the encoder states. So we go to encoder states dot permute 102, and what we have now is n comma sequence length comma hidden size times 2. All right, so you can look on the torch.bmm documentation, but essentially if we have them in this shape right here, then that if we do now torch.bmm on attention encoder states, this is going to do the matrix multiplication that we want, and this is going to be our context vector, and we're going to also do dot permute 102 right here. So let's see, if we multiply this with this, we're going to obtain n comma 1 comma hidden size times 2. All right, so that's just what it says in the documentation. If we do this multiplied with this using torch.bmm, we're going to get this as our output size. So we want 1 comma n comma hidden size times 2, and essentially what we're going to add then is this dot permute 102. So that's what it's going to do. So then now that we have our context vector, and remember this is for a specific time step in our decoder, since we're decoding one word at a time. So we're going to do the RNN input is going to be torch.catenate of the context vector and also the embedding, and we're going to do it along the dimension to the second, or I guess the third dimension of the tensor, so along the hidden size, so that we obtain this hidden size times 3, since the embedding is going to have hidden size context vector hidden size times 2. And then we want to send this through our RNN, and everything here looks all right. So everything else looks fine. And so trying to think if there's something I missed here. So just a quick recap, what we did, we want to, we want to concatenate this hidden states from our decoder with our encoder states. But to be able to do that, we gotta repeat the hidden states along each time step, which was from the encoder. And when we do that, we repeat it sequence length times. We then can concatenate these two, and we can send them through this small neural network, like one layer neural network, and to compute these energy states. Then we just run it through a softmax, and we get these attention scores. Then we got to do some reshaping so that we can use this Torch BMM, essentially, so we can multiply these attention scores with all of the encoder states. And we want to do that for all of our training examples, so that's why we do it in this way. And then we have the RNN input, which is essentially just a concatenation of the context vector and the embedding. We send this through the RNN, we get our outputs, we do our predictions as usual, and then we get predictions, and we also got to send out the hidden and the cell. Then let's see, so in our Seq2Seq, we have our output right here, we have our hidden, we have our cell, and one thing we got to send in now is the encoder states to our decoder. And so we have to send this out from our encoder as well, encoder states. And that was sent out, right? Yeah, encoder states and the hidden and the cell. So now that we have our encoder states, and we're going to send that in to our decoder at every time step, right? At the first time step, we're also going to send in the hidden and the cell. But when we predict one word, this is going to be overwritten by the new hidden and the cell from the decoder. But the encoder states right here is always going to be sent in. So it's always going to have this context in the way that we saw in the beginning of the video. And so I think that's it. See if there's anything we want to change here. So I actually think we don't have to do any other changes. So we can we can try to run this first, and we're probably going to get some errors, but let's see. Yeah, so one thing I didn't mention is that we're doing this for number of layers equals 1. I have done an implementation where you can choose the number of layers, but I found number of layers equal 1 to be best anyways, and I thought it would be simpler for the video because it would take quite a lot of time otherwise. But I'm going to have it in the description if you want to check if you can expand it to several layers. But we're going to have number of layers equals 1. And then what we got to do also is we got to remove the dropout from the LSTM, since it won't work if we only have one layer. And then it's also giving us another error, and then that dropout of a dropout. And I think that's because we send in dropout here, but the parameter is p. So if we rerun this now, it should probably work. Oh yeah, so it won't work actually. We need to also remove the dropout here, and now it might work. Yeah, so one more error is that here we had the sequence length comma n comma 1. If we want the 1 to be on this position, which we do want, then we need to do 1 2 0. So I just wrote the wrong thing here, and let's now try to rerun it again, and hopefully it works. Okay, so we can see that it's running, and it seems to work. What we can do now is that I have already trained a model on this, so we can do load model equals true. And let's do this blue score right here. I'm gonna take it up here, and we can do blue score on the entire data, and we can do just exit after this. So this is gonna take some while. I'm gonna run this blue score, and we'll see what we get. So just for some context, in the last video we got just below 21 in blue score. So when we have now added this attention mechanism, let's see what we get. So we can see that training with this added attention mechanisms substantially improves the performance, and then now we obtain a blue score of about 27.5, which is a lot better than 21. So yeah, thank you for watching this video. If you have any questions, leave them in the comment below, and I'll have a link to the GitHub where you can read the code. Yeah, hope to see you in the next video.